Hi everyone and welcome back to chemistry. This is Mrs. Hutchinson and today we're going to continue with our history of the atom notes, and we're really going to focus on subatomic particles. So the particles that exist within an atom. My guess is you probably have heard of all of these before, at least I would hope. We have discussed them in prior videos, but now we're really just kind of putting it all together. So we've got our subatomic particles. Again, they're the structures that exist within an atom. And we've got our protons, our neutrons, and our electrons. Our protons, as we know, have a charge of +1. Protons are positive. They have a mass of 1 atomic mass unit. Now, remember I told you we would define what an atomic mass unit is? Well, that definition of an AMU is it's equal to 1/12 of a carbon-12 atom. It's just basically a unit. So the mass of a proton is 1 AMU, and it's located in the nucleus of the atom. So if we've got, let's just say, we've got our most recent model based upon the gold foil experiment. So we've got our center nucleus. So there's our nucleus. And within that nucleus, we've got protons and neutrons. Outside of that nucleus, which we will get to, are electrons. So protons have a charge of +1, they have a mass of 1 AMU, and they're located in the nucleus. Neutrons are neutral, mass of 1 AMU, and again they're located in the nucleus. And our electrons have a charge of -1. They have what we would call 0 AMU because they're so small in comparison to the atomic mass of a proton or a neutron. Remember 1/1836 that of a proton or neutron. So essentially they really don't add as much to the overall mass of the atom. And they're located in the orbitals, which we will definitely discuss later when we get to Bohr's model and eventually our Schrödinger model or the wave mechanical model. But again, something else that I want to touch on here is that protons and neutrons, since they're located in the nucleus, we call them nucleons. Just another term to define where the subatomic particles actually exist. Now, if you don't have your periodic table out, get your periodic table out using your reference tables, because we're going to discuss where the subatomic particles are kind of hidden on the periodic table. They're there, they're just there in a very sneaky way. So if we take a look at that periodic table that you have now so kindly flipped to, what I'm going to do is focus on that big C in the middle of the periodic table, the one that they enlarged. So I'm going to do my best to actually draw it here. Not bad. Could be worse. So what is that big C? That's the atomic symbol. Okay, so that gives us some information on our periodic table. It gives us information of how they're going to abbreviate that particular element. But we really don't need that in terms of subatomic particles. What we really want to take a look at is for carbon, that giant 6 that they have, that's all colored in. Now again, art, coloring, all that stuff, not really my strong suit, but I really tried hard on that. So, what is that big 6? That big 6 is our atomic number. We're going to define atomic number here shortly, but it's actually a very important number. It tells us the number of protons that exist inside of the nucleus of that particular atom. We then have underneath the atomic number our electron configuration. So that tells us the total number of electrons that exist within an atom of that particular element. We also have the atomic mass up here, which is 12.011. That's a 12, by the way. And we will define that later. That comes really into play, helping us figure out number of neutrons. And then we have our oxidation states over here. They're selected oxidation states, and that basically tells us how many electrons this particular atom would likely gain or lose when it's creating a bond. So there's a lot of information here, and as we get further into discovering subatomic particles, you'll see really where all of these fall into play. But again, if we take a look at down here, we've got, say, beryllium. The oxidation state is +2. The atomic mass is around 9 if we round. Atomic number is 4, and the electron configuration is also, is 2, 2. So it tells us our total number of electrons is also 4. So now, let's really discover what is atomic number. So atomic number is that big bold number, this one right here. That's our atomic number. And it is defined as, or it is equal to, the number of protons that exist in the nucleus. Remember, protons exist in the nucleus, so that atomic number for nitrogen down here tells us that we have 7 protons in any nitrogen atom. It will never change. The number of protons will always be the same regardless of whatever nitrogen atom you are looking at. It is actually what defines an element. And it's also equal to the nuclear charge. Because if you think about it, the nuclear charge is actually defined as the charge of the nucleus. And, well, what's in the nucleus? We've got our protons, which have a charge of +1, and we've got our neutrons, which are neutral or have no charge. So the total number of protons gives us our total nuclear charge. So for nitrogen, the nuclear charge is going to be +7 because we have 7 total protons. Not too bad. And then last but not least, this isn't actually a definition of atomic number, but it does kind of make sense. It's also equal to the number of electrons because, well, atoms, should be atoms, are neutral. So remember this down here, this electron configuration? Well, if you add them up, you'll get a total number of electrons. 2 + 5 is going to give us our atomic number. So we can say that since all atoms are neutral, the atomic number is equal to not only the number of protons, but also our number of electrons. Kind of cool, kind of nice. Taking a look at the next subatomic particle, or the next number on our periodic table, would be our mass number. Our mass number is defined as the number of protons and neutrons. So it's equal to the sum of the protons plus the neutrons. It will always be a whole number because our whole number, the reason why it is a whole number is because we're talking about the total number of neutrons and total number of protons that exist in that particular atom. We can use it to help us calculate the number of neutrons that are present in an atom. So if we take a look at this, we have our mass number, and you'll notice what I did was I actually deleted the periodic table symbol of aluminum because I didn't want to confuse you. So mass number is equal to a whole number. It's equal to the numbers of protons and neutrons, and it can help us calculate the number of neutrons present. So let's just use aluminum as our example here. So that's silly. If we're talking about aluminum, aluminum has an atomic number of 13. And let's just say that our mass number is 27. So the top number represents our mass number, which represents the number of protons plus neutrons. And this bottom number represents our atomic number, which simply just tells us our number of protons. So looking at these, doing simple algebra, we can say, okay, well, how do we determine the number of neutrons? Not too bad. If we've got a number that represents protons plus neutrons, and we want to determine the total number of neutrons, we would simply subtract the number of protons and be left with our neutrons. That's an algebraic way of saying we just simply take the difference between these two numbers. We'll take our mass number, which represents our protons plus our neutrons, and subtract our number of protons, which is our atomic number, to get our number of neutrons that exist in that particular atom. Always going to be a whole number, you're never going to have half of a neutron. And we can represent this in many different ways. We could say 27Al, where that beginning number is our mass number. We could say Al 27, or we could go on to say aluminum 27. All of which those numbers that are following or prior to that particular symbol or name, those are the mass numbers. Do not get these numbers confused with the atomic number. The atomic number never, ever, ever changes. Mass number can, in fact, change because it depends on the number of neutrons that exist within that particular atom. So now, let's move on to atomic mass. Atomic mass, which we discussed and we saw actually on the symbol here down for carbon, that is our atomic mass. Our atomic mass, the reason why it's a decimal is because it is an average. It's the average atomic mass of all of the elements of that, all of the atoms of that particular element in the entire world. It's the weighted average of all of the naturally occurring isotopes. Now remember, isotopes differ in numbers of neutrons. We'll discuss that, I promise, further. But the weighted average of all naturally occurring isotopes. Okay, so since it is an average, it's going to be a decimal. It's very rare that you get an average that comes out to be a whole number. And it indicates the most abundant isotope on the entire periodic of that element in the world, I should say. So in this instance, carbon's atomic mass is 12.011. That means that that number is closest to our whole number of 12, so carbon-12 is our most abundant isotope on Earth. We'll discuss that later when we get to isotopes shortly. Not too much longer, we have to wait. And then let's discuss ions. We really will get into types of ions a little later, but I wanted to throw them in here because I felt like they were kind of important. So, ions. How is an ion created? It's created by gaining or losing electrons. So remember, the number of protons never changes. Number of protons in an atom never changes. You'll see later on, I may or may not be lying here, but for now, number of protons in an atom never changes. So, how is an ion created? It's created by gaining or losing electrons. If an atom lost an electron, it's going to become a positive ion. I mean, that makes some sense. Here's what I want you to think about. So if we lost a negative, let's just say, all right, we've got, remember atoms are neutral. So we've got 8 protons, 8 electrons. So if we lost an electron, we now have 8 protons and 7 electrons. So let's do some math. What's the charge of a proton? +1. So 8 protons that have a +1 charge. We then have 7 electrons that all have a -1 charge. When we do that math, we'll get 8 minus 7, leaving us with an overall charge of +1. So the math tells us what happens to the atoms that lose an electron. If you lose an electron, it becomes a positive ion. And conversely, that was silly, didn't mean to do that. If we take a look at atoms that gain an electron, so now instead of becoming 8 and 7, we've got 8 protons and 9 electrons. We've got 8 protons that have a charge of +1. We've got 9 electrons that have a charge of -1. So doing the math, we'll have 8 minus 9, giving us an overall charge of -1. Okay? So atoms that gain an electron become negative ions. Atoms that lose an electron become positive ions. That's the only thing we really need to focus on right now in terms of what an ion really is. How or why they gain or lose electrons, you're going to have to wait until a little bit later. So now what I want us to do is work on this particular worksheet. Using your periodic table and given the clue in each row, determine the number of subatomic particles and the name of the atom or element in each of the following atoms. So, atomic number, I gave you these definitions, you're welcome for that. Atomic number is equal to the number of protons, and because all atoms are neutral, they're also equal to the number of electrons. Atomic mass, in our instance, because we're looking on the periodic table, we're going to take the atomic mass and we're going to round to the nearest whole number. Just for this instance. So we're rounding to the nearest whole number for our atomic mass. That's going to give us our number of protons and neutrons. And to determine the number of neutrons, you'll simply take our atomic mass and subtract our atomic number. So, let's take a look at this particular example. If we take a look at oxygen on our periodic table, oxygen's atomic number is 8. If we take a look at the atomic mass, it's 15.9999999. It's going to round to 16, so our atomic mass winds up being 16. Our atomic number is always going to be equal to our number of protons. It's also our nuclear charge. Since all atoms are neutral, our atomic number is equal to our number of electrons. And here, last but not least, to find our number of neutrons, we'll take our atomic mass and subtract our atomic number. So we'll get 16 minus 8. So we will get 8. What I want to encourage you to do is not memorize the locations of where each number is on this particular table, but actually understand how to obtain the numbers from the periodic table. So go ahead, try the rest of these. If you have questions, there's one that in particular that I think is pretty tricky. If you can get that one, there's no way I can stump you. So go ahead, try these, and I will see you with our next video.